Welcome to 24 Hours of PaaS, the Growing Our Community edition. So this is the 17th session of the 24 Hours of PaaS, which is really exciting. And I'd like to thank you for joining us today for Alan Faulkner's session, SSAS Design and Performance Best Practices. So this 24 Hours of PaaS event consists of 24 consecutive live webcasts delivered by up-and-coming speakers and experts from the PaaS community. All sessions will be available next week on 24hoursofpaas.com. My name is Julie Cosmano, a Senior Program Manager at Microsoft, and I have a few quick introduction slides before I hand over to Alan. He will speak for 40 to 45 minutes, and then we'll move on to the Q&A where you can ask any questions you may have. If you're having any issues, just type question into the question pane on the GoToWebinar control panel and someone will assist you. In case you'd like to maximize your screen, use the Zoom button located on the top of the presentation window, and feel free to enter your questions in the Q&A field at any time. The questions pane is located on the right side of your screen. Once we get to the Q&A portion of the session, I'll read off your questions to the speaker. And since all attendees are muted, you will need to submit your questions by typing in the Q&A field. Note that there will be a short evaluation at the end of session, and please realize that your feedback is very important to us, so please take a moment to complete it, and it will show up on your screen. Next, I'd like to take a moment to thank our presenting sponsors, Microsoft, Cisco, and Dell Software. In addition, I'd also like to thank the support sponsors for this event, SQL Sentry, HP, and SolarWinds. The staging of 24 Hours of PaaS would not be possible without their support and dedication, and they are the reason this event is available free of charge. Now I'd like to bring your attention to the upcoming PaaS Summit. And it's actually taking place in Seattle, Washington from October 27th to 30th. And this year it will feature over 200 sessions with world-class SQL Server experts. Planned and presented by the SQL Server community for the SQL Server community, PaaS Summit is single-handedly the largest gathering of SQL Server and BI professionals. With over 5,000 attendees from all over the world, PaaS Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. And more importantly, PaaS Summit delivers on providing you with the answers to your SQL Server issues or questions, along with the knowledge, strategies, and skills you need to stay ahead of the curve. If you'd like to take advantage of $150 of discount code, please contact your local chapter. And you might want to optimize your savings by registering before the end of Sunday, July 12th. To find out more about PaaS Summit, please visit paassummit.com. And now I'd like to present the speaker of the hour, Alan Faulkner. He's a BI consultant at Pragmatic Works, and he's also an active member of the Arizona SQL Server User Group. He's obviously a speaker and has presented at various SQL Saturdays. And an interesting fact that you might need to know is that he is SSAS Master trained, so it's a perfect time to ask all your SSAS questions here. Over to you, Alan.
Okay, thank you, Julie. Thank you for the introduction, and welcome everybody. This is Alan Faulkner, and we are going to take a look at analysis services design and performance best practices. What's on the agenda? So a couple things we want to talk about, and this is going to start with our relational data source design, and then we're going to move into the Visual Studio side of things. We're going to talk about data source design, dimension design, cube design, partition design, and aggregation design, where we'll walk through several presentation slides on that and demos where appropriate. But in this session, we're specifically addressing analysis services multidimensional. But there are items that we are discussing that does apply to other flavors of analysis services, both tabular and multidimensional. Where there is commonality, I will try to highlight them, but we will not be doing a comparison contrast between tabular and multidimensional in this session. So if you've been out there and working, you know that Power Pivot is what you use to create your own data model from various data sources, modeled and structured precisely the way you need it or the way it fits your needs. With Power Pivot for SharePoint, you basically can leverage SharePoint or extend SharePoint 2010 or 2013 and Excel services to add server-side processing and collaboration and document management support for the Power Pivot workbooks that you would publish to SharePoint. Analysis Services Tabular. These are tabular models are database in-memory databases and analysis services. They use compression algorithms and multi-threaded query processing. The X-Velocity in-memory analytics engine, or also known as VertiPack, delivers fast access to the tabular model objects and the data by reporting client applications such as Microsoft Excel and Power View. Multidimensional Analysis Services multidimensional solution uses cube structures for analyzing business data across multiple dimensions. Multidimensional mode is the default server mode of analysis services, and it includes a query and calculation engine for OLAP data with with 3 storage modes, which is MOLAP, ROLAP, and HOLAP, if you've heard of those modes before. And that is used to balance performance with scalable data requirements. And starting with SQL Server 2012, an installation of analysis services can be done in either multidimensional, tabular, or Power Pivot for SharePoint mode. Each of these deployment modes uses a different engine and also works differently by using different storage structures and memory architectures. So each analysis services deployment mode supports different sets of data sources, development management tools, and query languages, etc. Really the point of this slide here is that with the different flavors of analysis, as you go to the right, you're going to get more scalability, but also as you go to the right, you're going to experience a little bit more of a learning curve from a development perspective. One of the things that we wanted to look at before we really get into the details is let's see how a typical Microsoft Business Intelligence application architecture would look. This will give you an understanding of identifying and locating some of the performance issues and bottlenecks that we'll discuss a little bit later on. The diagram shows a typical Microsoft BI application architecture, which has different layers shown from left to right. On the left layer, you have source systems or a relational data warehouse. In the middle, you'll have your analysis services or cubes where you're doing the processing and querying. And then on the right, you will have your BI applications, your reporting applications that are used to consume and visualize that data. Although typical Microsoft BI application architectures have each layer on a different physical machine, that is usually not the case. Typically, you'll run into something where you may have a analysis services and your relational data warehouse setting on the same box, and maybe your reporting application on another server, or a variation of those things. Really, what we want to talk about here is whatever your system architecture design is, or your approach is, you really need to make sure that your OLAP query performance is very fast, and that's usually the case with small cubes, but we cannot overlook the processing performance. When you're looking about targeting query performance, you also got to make trade-offs sometimes about processing performance. So with processing, this is what ensures data gets refreshed within, say, if you've got certain service level agreements within your organization. So basically, when we talk about analysis services performance optimization, we need to take care of basically 3 things: query performance, processing performance, and proper and adequate utilization of your hardware resources. So to address those performance optimization categories we talked about, so during processing, analysis services refreshes the cube or OLAP store with the latest data from the source systems and relational data warehouse and generates aggregates if any are defined. It also creates an attribute store for all the attributes of the dimensions and hierarchy store for all the natural hierarchies. Though it sounds like the processing time does not matter much in comparison with query processing, I would say it's equally important to make sure you provide the reports with refresh data within your defined SLAs within your organization. Query performance is also what is analysis services really known for. There are several ways you can improve analysis services or query performance. You should spend some time designing dimension and measure groups for optimal performance, create aggregations and bitmap indexes, optimize your MDX queries for faster execution. You never really want them to be in a low level or cell by cell mode and using subspace mode, and we'll talk a little bit more about that in some of the demos. Both processing and query performance is determined by how well you tune your resources for better throughput. You can specify the number of threads that can be created for parallel processing. You can also specify the amount of memory available to analysis services for usage, and it will also looking at better improving your I/O input-output systems, or placing your data and temp files on the fastest disk possible. So one of the things I like to talk about a little bit is how does Analysis Services answer an MDX query? And what we're talking about here is the Analysis Services internal architecture. And what happens is when we have a MDX query come in the door, the query parser has an XML listener which accepts requests. It parses the request and passes it along to the query processor for execution. Upon receiving the validated and parsed query from the query processor, the query processor prepares an execution plan which dictates how requested results will be provided from the cube data and the calculations used. The query processor caches the calculation results in the formula engine cache. This is where we're talking about right here. The storage engine responds to the subcube data request generated by the query processor. It first checks to see if the requested subcube data is already available in the storage engine cache. If it is there, it serves it from there. If not, then it checks if the aggregation is already available for the request, and from the aggregation store, it caches it to the storage engine, and also sends it to the query processor for serving up the query coming back out. So that's basically at a high level how a MDX query is answered. The thing about this is while you're troubleshooting, you need to understand which component is taking more time and needs to be optimized, such as the query processing engine or the storage engine. To determine this, you can use SQL Profiler to perform an OLAP trace and capture certain events which will tell you the time taken by these components. So now that we've talked about the kind of the architecture and analysis side of it, I want to specifically talk about relational data source design. And no matter how efficient your dimensions and cube design is, if your source system is not providing data fast enough, processing is definitely going to take longer than expected. So it is recommended that you spend some time designing and tuning your source system for better processing performance. Again, I'm going to say this, no amount of query tuning and optimization can beat the benefits of a well-designed data model. And I want you to say this out loud to yourself. No amount of query tuning and optimization can beat the benefits of a well-designed data model. Cubes are typically built on top of a relational data source that serve as data marts. In general, it is good cube design follows Kimball modeling techniques, and if you avoid some typical design mistakes, it will benefit you in the long run. A well-designed relational data source can make queries and processing of your cube faster. This cannot be stressed enough. If you have poor design on the relational data dimensional model side, it will only exponentially reveal its ugliness in the OLAP layer as your cube's usage and size grows. Now, you may be able to get away from some things as your cubes are small, but when they get large, this is where you start seeing some of these headaches that you'll get, because that is really where you have to spend the time up front. Really, the intent here is to highlight some of the most common design patterns and provide references where relevant or appropriate. Okay, so we're going to talking about these types of things here. So with a relational data source design, it's widely debated that the most efficient modeling technique is for reporting and analytics are star schema, snowflake schema, or even a third to fifth normal form or data vault models. All are considered by warehouse designers as candidates for reporting. Analysis Services is a unified dimensional model, or UDM, and with some additional features that support snowflakes in many dimensions and other complex relationships. But no matter which model you choose as the end user reporting model, performance of the relational model boils down to one simple fact: joins are expensive. This is also partially true for Analysis Services engine itself. For example, if a snowflake is implemented as a non-materialized reference dimension, users will wait longer for queries because the join is done at the runtime inside the Analysis Services engine. The largest impact of snowflakes occurs during processing of the partition data. So for example, if you have implemented a fact table as a join of two big tables, for example, separating order lines and order headers, Instead of storing them as pre-join values, processing of facts will take longer because the relational engine has to compute the join. If you choose a highly normalized structure, be prepared to pay the price. It's possible you can build an analysis service cube on a highly normalized model, but it isn't something I would recommend. In most cases, that price is paid at processing time, and in MOLAP data models, materialized reference dimensions help you store the result of the joined tables on disk and give you high-speed queries even on normalized data. However, if you're running other types of storage modes, queries will pay the price of the join at query time, and your user response times or your hardware budget will suffer if you're unable to resist the normalization structures. So just a quick, and most people here probably already know what this is, but one of the reasons I even present this is I like to talk about a couple of reasons why I think star schema is good for analysis services. First, the dimensional model is a predictable and standard framework. Report writers, query tools, and user interfaces can all make strong assumptions about the dimensional model to make their user interfaces more understandable and to make processing more efficient. The second strength of a dimensional model is that the predictable framework of the star join schema withstands unexpected changes in user behavior. Every dimension is equivalent. All dimensions can be thought of as symmetrically equal entry points into the fact table. And finally, the third strength of the dimensional model is that it is gracefully extensible to accommodate unexpected new data elements and new design decisions. So if you're not familiar with surrogate keys, typically where you use surrogate keys is an integer, small int, or big int field. A surrogate key should not be exposed for client tools, and a SK must be meaningless, meaning it has no analytic value. If you expose this key, your end users are likely to try to assign some meaning to it, which will be more than likely be incorrect and only cause you more overhead in the long run. Surrogate keys are internal to and referenced only in the relational dimensional model. When you want to transform data to create natural hierarchies, this is where we're talking about denormalized data. So just a quick example there, you can typically have repeating data, like for example, a date dimension would have repeating months, values, January, multiple times, February, and so on. You can transform that to create natural hierarchies. This will also cause your cube to perform both on a processing and query aspect as well. And you only want to provide the attributes that are needed into your model because they tend to will continue to add to those space requirements of your analysis services cube. So it is never a good idea to go out to your end users or business users and say, and with a list of all your attributes, say which ones you do need, because they're going to tell you they need all of them. Make sure that you only have those attributes needed in your model. Sometimes calculations can be moved to the relational engine and be processed as simple aggregates, which will have much better performance. There's no single solution here, but if you're encountering performance issues, consider whether the calculation can be resolved in the source database or DSV, preferably your source database, and be pre-populated rather than evaluated at query time. For example, instead of doing something like quantity times dollars to give you extended amount, just compute that extended amount right in the data source. And we'll take a look at that in the demo as well. With the use of views will help you provide an abstraction layer, and it is generally a good idea to build your dimensional model on top of on database views. A major advantage of views is that they provide an abstraction layer on top of the physical relational model. If the cube is built on top of views, the relational database can, to some degree, be remodeled without breaking the cube. Also, processing through view, depending on your relational source, views can often provide means to optimize the behavior of the relational database. So, for example, in SQL Server, you can use the no-lock query hint in the view definition to remove the overhead of locking rows as the view is scanned, balancing this with the possibility of getting dirty reads. Views can also be used to pre-aggregate large fact tables using a group by statement. The relational database model can even choose to materialize views that use a lot of hardware resources. So when we select data from a table, shared locks are placed on rows at the row key level. This row key level locking escalates to page level or table level depending on the amount of rows that are being selected or returned. To minimize the amount of effort by a SQL Server to manage these locks, you can specify no lock or a tab lock query hint in the query. So one of the things I'm going to jump over here is we're going to go back and forth here between our presentation and our solution checkpoint. And here, what I'm going to show here is this is just a database diagram of one of our measure groups. And in this case, this is our reseller sales. And in this, I just wanted to just show a few things. Here we have our fact table. So in this one, we've got our fact table right here. In this one, we also have something that we will come to appreciate within a multidimensional world is that we have the ability to use one table multiple times. And in this case, we're using our date dimension. And this is what we often refer to as a role-playing dimension. I did mention that I would talk about and learn how to spell or type, but I did mention that I would cover some of the things in tabular versus multidimensional. Role-playing dimensions are not available to you in tabular. You can join on a single table, but you only have one active relationship at a time. As opposed to a multidimensional situation, out of the box, you can have this role-playing dimension and they all are active relationships. Another thing that is also supported here is in a multidimensional world we have these parent-child self-referencing. This is not a possibility in a multidimensional either. So the other thing we mentioned here is looking at the calculations within our relational engine. The simple example here is that I want to show right here. We see that our order quantity and our unit price, if I'm multiplying 6 times 570, this will give me 3420. And then we can do a simple sum on this column within our analysis services solution to get this value. This scenario would perform much better than, say, creating an MDX calculation to say 6 order quantity times unit price to give me this. This is what we mean by putting the calculations in a relational database. Also, we were talking about views and how we can leverage the views using some of the query hints. For example, here in this view, this is a view for my reseller sales fact table, and I'm using a with no lock query hint, and this is assuming that we're doing batch processing, so we're not doing any real-time reads on this, and this is going to eliminate that locking overhead that we could potentially get while we're doing our processing. The final piece that I want to talk about here is you might ask, okay, how if I've already created my DSV, and this is what we're looking at here is our DSV for reseller sales, how would I go about replacing the table reference here to using my views? It is not too difficult. So we just say replace table with other table, and we would be using our, in this case, our internet sales, I believe, and we can just say replace, and then we would want to make sure that we have everything in order there and test it. But that's how you would go ahead and go about replacing that. Okay. So the next thing we want to talk about here is the data source design. And data source, if you've done any cube development, it's one of the first steps that you do is you establish basically where you're going to be reading your data from. And this is usually your relational data model that you're reading the data into the cube. OLAP databases, analysis services databases have several special requirements that are important to ensure trouble-free access for your source data. One is analysis services was designed and tested to work with a specific set of OLDB providers. Although other OLDB providers are available, and the data source wizard lets you choose any compatible provider, the capabilities can and the behavior of different providers can differ substantially. This is true even for different providers to connect to the same database. Therefore, you should use only supported providers. Another thing is that you shouldn't use the .NET SQL Client data provider because the Analysis Services server runs in native code. You can get better performance by using a native provider. Therefore, do not use the .NET SQL Client data provider. Instead, use the Microsoft Quality provider for SQL Server or the SQL native client provider. The next thing I want to talk about in relation to the data source design is, in addition to creating a high-speed network, meaning that you may have to work with your network admins to get jumbo packets enabled on your routers or your switches, there are some additional configurations you can change to further speed up network traffic. Under the properties of your data source, increasing the network packet size for SQL Server will minimize the protocol overhead required to build many small packages. The default value is 4096. With a data warehouse load, a packet size of 32K, this means assigning a value of 32767 can benefit your processing, and you don't have to change. You don't have to change this at the value of the SQL Server. You just override that in your data source. We'll again take a look at this in our demo. So the one thing I want to talk about here is where would I use that network packet size? We talked a little bit earlier about architecture, and I've got certain things on this box or that box. What I'm just going to show here is that two architectures that you basically want to look at. Now, I realize this is a very overly simplified architecture compared to most that you may deal with, but the objective is to demonstrate that if you have a single instance, in this case scenario A, with various SQL Server components on it, adjusting the packet size will have no real or net effect on the packet size being passed over the network, simply because the TCP IP stack is not in play here. So if your source system, in this case your relational data warehouse and your analysis services are both on the same machine, scenario A, you should consider using the shared memory .NET net library for better performance. The performance benefits come from the fact that it bypasses the physical network stack, and it uses Windows shared feature to communicate between SQL Server, client, and analysis services. Contrarily, on the right side of the screen here, scenario B is where we have more of a distributed architecture. Analysis services installed on a separate server than, say, where your relational dimensional data is. This can improve your query and processing performance by changing the packet size on the data source to allow for larger packet sizes to be transported over the network. So, really what I want to also point out here is during queue processing, data moves from your relational data warehouse to analysis services in what they call tabular data stream packets, or TDS. As data movement between the relational data warehouse and analysis services is normally high, we should configure this to have a bigger packet size, therefore less packets than using a smaller size or higher number of packets to minimize the overhead and breaking the data down into multiple chunks. So, and reassembling at the other end. You would just basically, to do this, to change the packet size, you can go into Connection Manager, and there is a property within there that we will show here in the demo where you would actually set that value. A couple other things that are to keep in mind here, to be aware of connecting source systems using data sources in an SSAS project. Sometimes when your source system is continuously changing and you want consistent data, you might need to pull data using a snapshot isolation mode, which in turn uses version store and SQL Server. In other scenarios, use the default recommitted isolation mode in order to avoid extra overhead and copies at the source system. In my experience, I have only so far done the recommitted, and we'll look at that here. Query timeout. With this problem, you can specify the query timeout for queries being run against the source system. I'm going to assert right here that if you're spending a lot of time fiddling with this setting, you're probably looking in the wrong place. You probably need to be looking at, say, updating statistics on your database side, your relational database, or maybe you've got some indexes that need some attention. But if you're spending some time here, you're probably spending it in the wrong place. The number of connections. This is where you can specify the maximum number of connections that analysis services can create in parallel to pull the data from the source systems during queue processing. This really helps in queue processing to run in parallel by creating multiple connections to refresh several dimensions and facts in parallel. The default value for this is 10, and you should consider increasing this if you have a cube with lots of dimensions and your source system, or where your relational data warehouse is setting, supports more parallel connections. This will greatly improve your queue processing times. And then impersonation, this allows you to specify the credentials that will be used for connecting and pulling your data from source systems. So we're going to come back into our solution here and look at our data source. As I mentioned, the data source is one of the very first things we create within our analysis services design. And I am just going to open this guy up, and we're going to look at a few things here. As we mentioned here a little bit earlier, we talked about the isolation. In this case, we've got read committed or snapshot. Read committed is our default. I have not had anything that has required a snapshot. But again, if you have something where the source system is changing over and over and over and you need to keep those history or those snapshots, snapshot is the way to go. As I mentioned, the query timeout is where we set the value in seconds for a query timeout. I would submit again here is if you're spending a lot of time on this, you're probably looking, you need to go look elsewhere. Maybe something is going on in your database, your data warehouse area. And here on a maximum number of connections, this is the number of connections that are launched during processing that allows pulling the data from our relational data source, database to pull the data into the queue. And in here, here's our impersonation information. Again, this is what is being used to basically authenticate ourselves to, or authenticate the credentials to the relational data warehouse. So the one I typically use is either use the service account, or I have actually used inherit, and I believe this is by default where it is. But in inherit, this will let you use the impersonating settings of the analysis services database that contains the data source object, and that is probably the one I would recommend, either this one or this one. Again, if you're going to use your analysis services service account, it will have to have read permissions on your relational data warehouse or database. Also wanted to really quickly cover where we look at and change that network packet size. So how I got there is I'm in here, I edit my connection string, and if I go to my all, right here there's a property called network packet size, and we're looking at it right here. So this is this guy right here. You can see that's 32767, and that will allow us that full maximum 32K size packets over the wire. Okay. Now, I'm talking about dimension design best practices. A well-tuned dimension design is one of the most critical success factors of a high-performing analysis services solution. It is important to ensure that the attributes, relationships, and the hierarchies correctly reflect the data and match the needs of your end users. The dimension of the cube are the first stop for data analysis, and their design has a deep impact on the performance of all measures in the cube. Dimensions are composed of attributes which are related to each other through hierarchies. Efficient use of attributes is a key design skill to master, and studying and implementing the attribute relationships available in the business model can help improve cube performance. So when we start talking about dimension design, attribute relationships are an important part of dimension design. They help the server optimize the storage of the data, define referential integrity rules within the dimension, and control the presence of member properties and determine how MDX restrictions on one hierarchy affect the values in another hierarchy. So you can obviously see for these reasons it is important to spend some time defining attribute relationships that accurately reflect the relationships in the data. We did talk about this a little bit earlier. We do not want to use attributes. They're not going to be used. I think I'm not going to beleaguer this point. but it's really true, especially if you have attributes that have the attribute hierarchy enabled set to true. This is just going to add more complexity to your cube, and it can actually unnecessarily make the end user experience a little bit more difficult than it needs to be. And this last one here, which is a mouthful, it says, do not create hierarchies where an attribute of a lower level contains fewer members than an attribute of a level above. And you're going, what did you just say? Really, the next screen or the next slide is actually going to explain this a little bit better, and I'm going to use a simple date dimension to explain this. When I design hierarchies, I think of it in a triangular shape. And at the top of that triangle, it's going to have the fewest members, so I'm using this date dimension, and in my year here, I have 2014. In my year quarter level, I have 4 records, or 4 values. In my month, I have 12 in this case, and then at the date level, I would have up to 365. So the smaller the number of the attributes are at the top, and as you expand to the lower levels, the number of attributes increase. This is the way I like to think of a natural hierarchy. This should be true in any hierarchy that you are developing if you're trying to create a natural navigation path within your dimensions and within your hierarchies. And the more you follow this type of design, the better your cubes are going to perform on both processing and querying. So because there is no all member, each non-aggregatable attribute will always have some non-all member selected, even if it's not even specified in the query. Therefore, if you include multiple non-aggregable attributes in a dimension, the selected attributes will conflict and produce unexpected numbers. So you really only want to, you really don't want to do that. Using key columns and those types of values, usually a single key column is sufficient, but sometimes multiple key columns are necessary to uniquely identify members of an attribute. So, for example, it is common in time dimensions or date dimensions to have a month attribute include both a year and month values as the key columns. This is known as a composite key, and it identifies January of 2013 being different than, say, January 2015 and January 2014. In the case of date dimension, it also helps you properly sort the date values in client tools, for example, like Excel, when used to navigate or browse a cube. Key columns of properties specifies one or more source fields that uniquely identify each instance of the attribute. The name column property specifies the source field that will be displayed to end users. If you do not use or specify the value for the name column, it is going to automatically set the value of the key columns property. That's what will be displayed. And the value column is used for other things within your analysis services. It's typically used for calculations. Unlike member properties, this property of an attribute is strongly typed, so providing increased performance when it is used in calculations. And when we're talking about using the keys and attributes, I always try to say you should stick with, say, integer-based or numeric-based keys if you can. Another rule of thumb is if you're going to have something that's more than a few thousand records, you definitely want to consider your key structures with integer-based values. Setting the relationship type property. The relationships between members of some attributes, such as dates in a given month or the gender of a customer, are not expected to change. Other relationships, such as salespeople in a region or the marital status of a customer, are more prone to change over time. So this is where you would start working with the attribute relationship type. You would set it to flexible for those relationships that are expected to change, and set relationship type to rigid for relationships that are not expected to change over time. When you set the relationship type appropriately, the server can optimize the processing of changes and rebuilding of aggregations. By default, the user interface always sets a relationship type to flexible. One of the key things that I have run into is that people will use the error configurations to get around some type of processing error while they're developing. And unfortunately, I have run into situations where they forgot to go back and reset this, and they were having very bizarre results come out of their cube, they could see that there was something going on with the data, but they couldn't figure out what it was, and it was basically creating data integrity issues. My recommendation is basically I would avoid using error configurations within key duplicates or set the ignore errors on dimensions. This is just really not a good idea because, again, as I said, it will create data integrity issues, and if you forget to reset it, you'll get into production with it, or you potentially get in production with it, and it could cause you some issues there. And we always want to try to create one user-defined hierarchy in each dimension that does not have a parent-child hierarchy. So most dimensions contain some hierarchical structure to the data, which is worth exposing in the cube. Frequently, the cube wizard or dimension wizard will not detect this hierarchy. In these cases, you should have defined the hierarchy manually. And one last thing, this is talking about the instance selection property, and this is one of these properties that I ran into when I was working with a client that their entire user base was using only Excel to interface with a cube. So we had some dimensions that had a large number of attributes. So what we're talking about here is, if you've kind of used this table as a rule of thumb, if you're going to have something greater than 5,000 members, for example, you want to put a mandatory filter on it, so it will actually must always be filtered so that you're not always having multiple values scanning on those attributes. So we're going to walk in and step into the solution here, and first thing here is I want to talk about is, we've got some hierarchies here, but it's more specifically what I was talking about a little bit earlier is these attribute relationships. This is where we want to set our attribute relationships and then the relationship type. In this case, we're setting it to rigid because we expect the same date to always report to the same month. And also remember the number of attributes. In this case, this is our lowest level, so it goes from left to right. My lowest level has a little over 2,100 members, and then in my next level up, I have a member count of 72. As if we move right, we'll see this here, 24 and 12. On the contrary here, I'm going to show you something with say a customer, and here's one that's indicating that the relationship type is flexible, because it can happen that a customer can move from one postal code to another, so that it would be likely to change. But up here, we have these set to flexible because the postal code we're expected it will always be the same city. The city will be the same state province. And the state province will always be into the same country. Okay. All right, talking about cube design best practices. Well-designed cubes will better match the needs of your end users. The following practices can improve usability and also performance of the cube. Avoid including unrelated measure groups in the same cube. I've had an experience where there was a cube that was in a competing tool, and they wanted to move 5 of those cubes down to one analysis services cubes, and my question was, why are we moving 5 cubes to 1 cube? They said because that's what we want to do. We want to do 5 to 1, not 5 to 2. So really you want to look at whether your measure groups are really related to the data. If you don't look at that really closely, this actually can adversely affect the query performance of the cube, even queries that only use a single measure group. So if your DSV contains many fact tables and they will not be used together, consider creating multiple smaller cubes containing topic areas that are used together. Excuse me. Avoid creating multiple measure groups that have the same dimensionality and granularity. This is another way to really adversely affect your performance. This is the presence of many similar measure groups that presents a more complex model to the end user by dividing data on common subject. Instead, you should consider creating a single measure group that contains multiple partitions. And the common exception to this guidelines is distinct count measure, which for performance reasons, by default, will be put in their own measure groups. So let me look here. This again refers back to what we were calling a little bit earlier role-playing dimensions. You always, if you have the opportunity, date is a good example, you want to use this same dimension table or the same table multiple times instead of creating duplicate tables within your data source or your DSV. Avoid having cubes with a single dimension. This is usually an indication that you're probably building a cube against a very large flattened table, and there probably are scenarios where there are more business entities within that big table, and you can split that out to actually have more dimensions instead of single one. So that's one you want to avoid and look at potentially breaking something out a little bit more or understanding the data design or data source or the business process a little bit more. And from data type of measures must be large enough to hold the largest aggregated value, the all value, but should be no larger than necessary so that you can reduce the storage costs of those values. So measure groups, again, we've talked about this a little bit, but we're going to jump in here and we're back into our solution. And we talking about this in our DSV, but here's just another example of that role-playing dimension. You're using this 3 times, so we're basically leveraging that date dimension to drive an order date, due date, and ship date in this case. So we've got 3 date dimensions being provided by the single date dimension table here. Then as far as distinct count measure groups and those types of things, those are created by default. The measure groups in this case, for example, we can see that the internet orders created a new measure group. It's also based on internet sales, but it created its own measure group because the aggregate function that we are performing here is a distinct count. Okay, partitions, real quickly, enhance query performance, improve processing performance, and facilitate data management. Partition slicing is because data sources, the data sources underlying our cubes, and even the cubes themselves can become very, very large in physical size. Storage can become a very significant consideration within cube design strategy. A partition is basically a physical file on a hard disk that contains a subset of the data included in the analysis services database. Partitions separate measure group data into physical storage units. Effective use of partitions can enhance query performance, improve processing performance, and can facilitate the data management as we were talking about a little bit earlier. You must often trade off between query processing performance and your partitioning strategy. One of the things I like to talk about partitioning strategy is, if you can, having your partition strategy in your analysis services cube align with the same partitioning strategy you have in your relational data source design, you're going to get better performance and throughput on your processing side than if you have it, say, a little bit different than that. This one right here, this is the reason I put the asterisk, is I've actually seen partitions have more than 20 million rows. I've seen some with 40, 50, 60 million rows, and they actually perform pretty well. It's just kind of a rule of thumb. You also want to avoid having small partitions and too many of them in a small measure groups. You probably want to consider combining partitions if you have a bunch of small ones. And you may also, from a partitioning of a distinct count measure group, you want to do that, say most often, how the dimension will be used in the query against the distinct count measure group. So when I come back to the solution here, I am going to look at my partitions, and this is just an example of a couple of things here. Is in this one here we have our estimated rows. This is an important piece, and how this is being done, I'm using a tool called Bids Helper that is downloaded from Codeplex, and this allows me to set these estimated counts. This will also help you improve your query performance, but also your partition slicing. If you're not familiar with it, the slice refers to what we're talking about here in our where clause. So the slice in this case is anything less than December 31st of 2005. And likewise, the other partitions in this measure group are done the same way. We have an order date key range. And in this case, we have 4 partitions here on our reseller cells. likewise we have that. Okay. Aggregation design, so what are they? It's a copy of the data in your fact table, pre-aggregated to a certain level. It's created when the cube is processed and it is stored on disk. You can think of it being similar to the results of a group by query in a SQL statement or a SQL query. It makes queries fast because it means analysis service does not have to aggregate the data as much at query time. So why build them? Aggregations are the single most important feature in analysis services regarding query performance. Every cube with a fact table of more than a few million rows would benefit from aggregations. And I'm going to move on. Here's the one thing that I want to say. If you create too many aggregations, like right here with this one here, if we had a aggregation design based on just this, we could answer all these values here. But if I create aggregations in addition to that with a 40, 60, 100, and this type of stuff, I basically explode my aggregation, and I can actually increase my processing time if I do something like this. So it's always best to look at what is minimally best and gradually build from there. So one of the things I'm going to talk about here is just we did talk about the estimated row counts, the partitioning size, usage-based optimization, the query log. This isn't something that you actually define on the Visual Studio solution. This is at the server level, and how I get there, in this case, I'm using my analysis services instance, and I'm going to the properties and the general, where I am actually setting that OLAP query log for usage-based optimization is right here. These values in here, it's going to allow me to create, the query log using these values right here. And one of the things that will allow me to do is it will allow me to create aggregation designs within my Visual Studio solution. In here, I can say if I wanted to create another usage-based optimization, it would actually go in and start using those values to run through that, and now it's going to prompt me for that, for my user ID, for the SSAS log, and I don't remember it offhand, but what this is going to do would go out and read any of those queries that were logged that usage-based optimization table and create aggregates or aggregations based on that. And I have used a combination of initially letting analysis services build its aggregations, and then in a few weeks' time after I've had some usage-based optimization statistics collected, also run that usage-based optimization to create and combine aggregations to kind of get a best of both worlds scenario.
Hi, Alan.
Yep.
Just a reminder that we do have 7 minutes left,
Okay.
but we don't have any questions yet, so feel free to continue.
Okay. So this is really coming to the wrapping up point of this. So why are the best practices important in analysis services? Well, we've talked about processing performance. During processing performance, analysis services refreshes your cube or OLAP store with the latest data from your data source. The sooner the cube finishes processing, the sooner the data is available to your end users. Therefore, you can provide the reports with refreshed data to them. Querying performance. Spending time in designing dimension and measure groups for optimal performance will create a better end user experience. If the data is returned quickly, end user analysis can progress relatively unimpeded. And then around our analysis, our instance and hardware resources, both processing and query performance is determined by how well you tune your resources for better throughput. So understanding or working with somebody who understands how to optimize disk configurations, RAM utilization, etc., will assist in lowering the capital needed for additional hardware resources. Lastly, you will save yourself a lot of grief by doing these things up front in your design as opposed to after the fact. Otherwise, you'll spend lots of your time working to uncover and diagnose the root cause and performance bottleneck, and it can be very painful at times to get that done. So I am going to say at this point, that kind of wraps up the session, and I am available for any questions, and I'll pass it back over to Julie.
Thanks, Alan. That was great. I learned quite a lot of new tips over there, so that was good. Okay, so we're just waiting for questions to come in. actually have an ice up a question here,
Okay.
just to lighten it up a little bit. Okay, so a lot of the companies that I worked with in the past as a consultant, quite a lot of them are kind of like small shops, so they only have maybe just a few databases, and they might only have, say, standard edition of SQL Server, and they obviously don't have too many people managing databases or particularly SQL Server, and so they decide to just spin up everything on on one single server.
Right.
So SQL Server on one server, sorry, the database engine in the same server as SSIS, SSAS.
Yep.
To what point would you advise this typical sort of small shop to hopefully have kind of like a
maybe it was kind
more
of
server,
yeah,
to scale out?
I would, if you're going to be dealing with, let's say, I'm going to say this, there's a couple rules of thumb here. If we, just from a data volumes perspective, let's put that aside for the moment. Let's say we're going to have concurrent users. We expect 50, 60, 100 concurrent users. That's when I would start really considering moving to a more distributed architecture with, say, I have my analysis services dedicated on one box, and then my relational source and the other SQL Server components installed on the other one. I would separate it out. And you may even look at potentially doing something like doing analysis services and reporting services on that one box. Or I would say because if working with analysis services, it is a memory consumer. So if you isolate that and put it on a dedicated box, I think if you're looking at somewhere above 50 concurrent users, that's probably something you want to consider. From a data volume perspective, if you're talking about fact tables under the, say, the 100,000 range, you're probably okay all on the same box. But if you start getting into a range of a couple 100,000 on up, you're going to want to look at moving that off as well, so that the processing can benefit from the packet stuff, because again, you're going to be in memory contention, because everything's going to be competing for memory on that one box. And when you go into processing mode, memory is a big issue. So that's when I would also be looking at putting it on another box. Those were the two primary things I would be looking at.
Okay, perfect. So we have one question here,
Sure.
and we do have only 2 minutes to go through this.
Okay.
On the database side, I can insert or update data in any of my partitions. Do I have to reprocess all the SSAS partitions if the data changes?
You do not have to process all the partitions, only the partitions where the data changed. So you would not, right. Let's say if I had 4 partitions and only the data changed in one, I'd only have to process that one partition.
Mm-hmm. And we've just got another question here.
Okay.
If there's only one server available, what's the minimum recommended hardware if we're only using one box for the whole services?
Yeah, that's an interesting question. I would say from a RAM perspective, you're probably wanting a minimum of 32 gigs, a minimum. You definitely want a quad-core CPU if you can get it. You want the fastest disk possible that you can get, because again, it's going to have to read the data and process that. I think really where you want to be investing your time or your money would be RAM, CPU, and fast disk.
All right, perfect. So with that, I'd like to wrap up the session. Thank you, Alan, for a wonderful session. That was really great, very insightful. And thanks everyone for attending. And if you'd like to join us in social media, you can join us on Twitter at past24 HOP. And next coming up is Data Pages Allocation Units IAM Chains, oh my, with Brandon Leach. Thanks everyone, and enjoy the rest of 24 hours of PASS.
Thank you.